What's up, trigonometry? This is Mr. Carlson, C-squared mathematics, and hot dog. We are in the last lesson of this week. So, good job. 7.4 polar graphs. We basically informally went through the Desmos activity and how basically polar equations relate to how the graph looks. So which values of the polar equation affect the polar graph. That's what you should have done during the polar graphs exploration, Desmos activity. Now, when you're getting here, it's the more formal math and the more intricate parts on how to actually graph the graph. Now, let me be clear, I will still be utilizing Desmos, but there's some parts here on Math Excel even that's going to ask you certain questions that you cannot necessarily use Desmos for. One of which is being like a table. How do I create a table for a polar graph? And then other things such as tests for symmetry. So when I want to test something for symmetry, I need to know specifically if it actually is this value. And that's something that Desmos just cannot offer. So we are still going to be using the formal math. And then at the same time, when we actually go graphing them, we're going to be utilizing Desmos. And then we're also going to be utilizing the specific steps and the specific values in which makes a function, specifically a polar function, the polar graph, an actual graph. So which values, depending on how they relate to other values in the graph, why do they make, let's just say, a limousin or a rose or a different polar graph, a circle, okay? So let's get started. Objective central question. How do I graph a polar equation using points, but also using what we call symmetry? So those are the two main things that we're going to be doing today. We're going to be doing a little bit more than that, but basically points and then symmetry. So how to calculate it on the TI-84. If you have a TI-84, that would be wonderful. Here are the steps. But also Desmos is just very basic. You can just straight up plug it in. But here's the steps to the TI-84. For those of you who are interested or have a TI-84. By the way, I highly encourage you that if you're going to go into like a sciencey or an engineering or a math degree or anything like that after high school, then it is well worth your time to buy a TI-84. It's just going to be well worth it. I highly encourage you to buy a TI-84. Even if you have a 36X Pro, I would just buy an 84 just because if you're going into like a math sort of degree. Okay, not necessarily medical, but just a math sort of degree. You may also use Desmos. So if you go to Desmos, type in -2 cosine 5 theta. What should you get? So let's go over there. So R equals -2 cosine 5 theta. I get this. Very beautiful. Okay? Very, very cool indeed. So I can make, theta equals like 5 or something. Actually, I can't do that. Let me say, yeah, let's just make this R. We did this yesterday. So R equals 5. And I can really just change this however really I want. Okay? And that's the cool part, and that's what I really, really like. You know, I can change that however I want. But regardless, if I don't even want to do that, you can just do the actual process the same. Okay, just the same thing that you're given. So what is this? This is 5 petals. It shouldn't be a surprise because if we were on Desmos before, we noticed that this right here, the 5, that tells me if that's odd, you will have 5 petals. Okay, and the -2 is what tells me the absolute value of that. It tells me it goes to the radius of 2 there. So awesome. And this is also what it will look like. Okay, so now this is probably one of the harder examples here. By hard, I mean like extremely freaking tedious. Like I almost debated like whether or not I want to show this to you. So you're welcome. I am going to. But it's just like, man, I really don't want to teach this right now. And maybe some of you, especially one student who will remain unnamed, is probably thinking in their mind, yeah, so why are you teaching us? Great question. that student? Great question. Because I love you. That's why. And I like you knowing things. So how to do this, Math Excel will probably give you some sort of plotting device like a table. And so this is how you graph an equation using the plotting method. It is the worst method. I highly suggest you never plot it like this, but the problem is Math Excel will more than likely have a couple questions like that. I'm given 4 cosine of theta with theta in radians. So what I'm going to do is make a table. Not as crappy as that. So let's try this again. That's actually pretty good. Make a table. I'm just going to pick a couple of points. I'm not going to go ad nauseum and just do all these points together to make the graph. It's just ridiculous. I'm only going to do a couple of points to show you. This is my actual equation for cosine of theta. And then this will be my point over here. So r comma theta. Okay, so let's just pick a couple of these. Let's just pick 0 radians. Let's pick pi over 2. And then, yeah, let's just pick pi. I think those are good. I'm just going to pick those 3. Let's do that. So when I put 0 in here, what I get is going to be 4 cosine of 0. And cosine of 0 is just 1, so that means it's 4 times 1, which equals 4. Now, what does that mean? That means my point here I had for 4 for my r, and my theta is 0. So that right there, I can actually plug in. So 4 comma 0. So 4 comma 0, I plug in my theta first. So where's my theta? Well, it's 0. And then 4, it's going to be like out. Let's make this 1 here. So that's just going to be 1, 2, 3, 4. So it's going to be like somewhere right here. That's 4 comma 0. Okay, let's do pi over 2. So if I plug in pi over 2, this is cosine of pi over 2. Cosine of pi over 2 is just 0. So this is 4 times 0, which just is 0, which means my point is 0 and then pi all over 2. So 0 for my r, but pi over 2, that means it's going to be literally just right here on the origin, just straight up. Okay? And then pi, so this is 4 cosine of pi. 4 cosine of pi. Cosine of pi is actually -1, so I'm going to times by -1, and just this gives me -4. So what's my point? My point, I got out -4, and then I plugged in pi. So think about this. This is probably not the best points I should have done right here, but pi is all the way over here, but then -4 is just flipping back here. So it's really these 2 points, but it does not matter because it's going to look something similar to this. It's just going to be a straight up circle. I know I'm butchering that really, really bad, so I'm going to go to Desmos real quick and show you. But that's basically, when they ask you to plot points, that's really what you're going to be doing, is literally just plugging in points. Okay? That's what I mean by difficult. I mean, it's just difficult to get through because it's so freaking boring. Like, so let's plug it into Desmos. I have 4 cosine theta. Like I said, boom. The bad thing about this is what I don't like about the polar graphs. You can't have points. Like, you can't click on the points, you know, like you can with X, Y, rectangular coordinates. Whatever. So my radius here is actually 2. So 2. Cool, right? Maybe. Now remember, it's cosine. It's on the x-axis, so it's cosine. If this was sine, it would be up here. So if I actually change that to sine, it would be on my y-axis like that. So just FYI, that's something we learned yesterday. So that's all I'm going to do there. I just plot that. It is a circle. Okay, it is a circle. And I could show you, and I can change that to an actual rectangular coordinate system. And sometimes it may ask you to change this to a rectangular coordinate equation. Okay, we can definitely do that. Okay, all we have to do is just change the sign to y all over r, and then go to town. So if I wanted to do that, it would be r equals 4, and then sine is y all over r, and then go to town. I know this was cosine, so let's just change it to x because it was originally cosine of theta, right? And so this is r squared 4, and then this is just x. And so then r squared is x squared plus y squared, and then we can subtract the x over equals 0. We can perform completing the square on it and so forth. So this is stuff that we already learned in the previous couple days. So just letting you know, you could still take it into a rectangular coordinate equation, but that's not what we're going to be doing right now. So this is basically the circles. So this is the formal notation. If the graph looks like this, if your equation looks like this, then it's going to be a circle. Okay. Notice how cosine is with my x's, and then my x-axis, and then my sine is with my y-axis. Your a value is the distance, basically your diameter. Okay, that's really what it is. So your a value is your diameter of your circle. Okay, split that puppy in half, you get your radius. Okay. So like I said, you can just always check, or by converting the equation to rectangular form, just like what I said. Now here, tested symmetry, this is probably the other big thing that Desmos really can't help us out with. These tests with symmetries, there's 3 tests, and they're each with regarding to a certain origin, or a certain pole, or a certain symmetrical axis, if you will. So the first, if I say it's symmetrical to what we call the polar axis or the x-axis, they mean the exact same thing, then what you're going to do is replace theta with negative theta. If equivalent, then the graph is symmetrical. Okay, so really you're going to start seeing with all of these, the second and the third, it will always say if equivalent to your actual graph. If you get the same graph out, then it's symmetrical. If it's not the same graph, if you don't get the same graph out after you do this test right here, because this right here is your test, then it's not symmetrical according to this. Make sense? Okay. The second thing, symmetry with respect to what we call the line. That's also what we call the pi over 2, and then the y-axis. So sometimes I just call it the line, and that's just the pi over 2 or y-axis. So here's the test. I would write that down if I were you. This is the test right here. So replace r and theta with negative r and negative theta. If it pops out to be the exact same graph, then boom, it's symmetrical to what we call the y-axis. Mostly this is going to be for cosines because it's an even function, and so the negative theta won't necessarily won't affect it, if that makes sense. Third, here's my test. I want to replace r with negative r. Okay, so here's my test, r with negative r. And so again, if it's equivalent, it's going to be symmetric to the pole. So the pole is what we call the origin. This is also what we call the identity line, by the way, in x graphs, rectangular coordinates, okay? So you don't necessarily need to actually write down the graphs here. Just write down kind of what I've underlined. And this last thing. What the junk? Why is it not showing up? Okay. I guess I'll just show it to you on the next slide. So get this down and pause it if you need to. I'm going to show you. Now this symmetrical graphs, basically what it means is this. If it passes the test, then it is symmetric. But if it fails the test, here's the important part, it may or may not be symmetric. Do you understand? So on Math Excel, pay very close attention. On Math Excel, it's going to give you these tests. Is it symmetrical to the pole, to the polar axis, to the line, the y-axis? Is it symmetrical? It will tell you yes, no, may or may not be. you will never, ever, 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 never, ever, never, 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 ever, ever say no. Okay? You'll never say no because because when you go through the test, which Math Excel is wanting you to actually perform the test, like what I'm about to show you right now in this example, what you can only conclude is yes or maybe. You can never conclude no. Now, obviously, we can graph it, right? And then you're probably thinking, if we can graph it, we can tell whether or not it's symmetrical, Mr. Carlson, so it's no. Yes, but Math Excel will not want you to graph it to find symmetry. It wants you to use the test to find the symmetry, not the graph. So it'll never be a no on Math Excel. It'll either be yes or maybe. Make sense? Okay. So let's continue on this. Let's test it out. So the first test, ready? The first test is going to be with my polar axis. My polar axis. Okay. This test said I'm going to take theta and then I'm going to put a negative in the theta. That's what it says. Okay. So let's test it out. It's r equals 1 minus cosine of negative theta. Since cosine is in fact an even function, what that means is this is going to pop out to be r equals 1 minus just straight up cosine theta. And since it is the case, like this is my answer when I perform the test, and it's exactly like the previous or my original equation, that means it checks out. Okay, it checks out. Perfect. So now I know it's symmetrical to the pole. Now, is it symmetrical to the polar axis? Is it symmetrical to what we call the pole or the line? So let's go to the line. So line, pi all over 2 first. Okay, what this says is I'm going to take r and theta, and then I'm going to change it to be negative r and negative theta. That's what the test is. Okay, so let's try it out. I'm going to change r to a negative r, 1 minus, and I'm going to change this theta to a negative theta. Do I get out my original graph? Well, while my theta pops out just like my original, my r does not. Okay? And so since I have this, even if I divided everything by a negative, I definitely don't have the original equation back. So this right here is a no bueno. Okay? Does not check out. It's not symmetrical to the line. Remember, the line is the pi over 2 line. The polar axis is the x-axis. Now let's check to see if it's symmetrical to the pole. The pole is like the identity line, the diagonal line. My test is r to negative r. Okay? So if I change that to negative r, this is 1 minus cosine of theta. Of course, this is not like it. Even if I change this up to say r equals cosine of theta minus 1 and just divide everything by negative, it's still not like my original. So that means this is only symmetrical to the polar axis. What is this going to look like? I'm not going to waste your time to graph it by plotting the points. You can use Desmos. But essentially, if this is, let's just say this is 2 here, okay, and this is about 1, essentially what it's going to look like is this. Something similar to that-ish. Okay, you can go on Desmos real quick and plot it. It's just going to be something similar to that, roughly. Okay, it's really hard to draw these, especially with a laggy pen. But yeah, so as you can see, it is symmetrical to the polar axis, my x-axis. I can flip it back and forth. It's not symmetrical to my y-axis, and it's not symmetrical to my line, or sorry, my pole. So not symmetrical to my line, pi over 2, and definitely not symmetrical to my pole. But it is symmetrical to my x-axis. Make sense? So that means for these, you would just say maybe, and then you would say maybe. You would not say no here, even if you did graph. Okay? Let's erase, and let's just continue on to go through these graphs. Okay? A lot of times they're going to ask to test for symmetry. So I'm just going to go through the test for symmetry on this next one real quick just to test it out. And then we're going to do a little bit more math because this looks kind of complicated, right? So we're going to do a little bit of math to see if it's either an inner loop, if it's a heart shape, if it's dimpled, or if it's no dimpled. Because again, like I said, Math Excel will want you to answer these questions. So this is the basic formula here. Looks something like this, something that you did on the exploration for Desmos activities. And then you have all of this. So if it's an inner loop, what you have is A over B is less than 1. So if you take A and then divide it by B, and if it's less than 1, then that means it's going to be an inner loop. If you take A over B and it's equal to 1, it's what we call a cardioid. Okay, you also learned that in Desmos. Okay, if you take A over B and then it's actually in between 1 to 2, so if it's like 1.5, 1.7 or something like that, or 1 3/4, then that means it's dimpled but with no inner loop, and then that means no dimple right here for my last one if it's actually greater than or equal to 2. Okay, so we're going to actually perform this one and we'll see what it looks like. So I notice it's sine. That means I know it's going to be vertical, up and down. So let's go through the test for symmetry first and then go to town. So the test for symmetry, the first thing I want to ask is, what about the polar axis? Is this symmetrical to my polar axis? Again, my polar axis says one thing, and it says that I can take theta, and if I put a negative theta there, and I get the same equation back, that means it is symmetrical. Okay, so r equals 1 plus 2 sine of negative theta. Okay, sine of negative theta is not even, so what I get is r equals 1 plus, since it's not even, I get a negative out front, so minus 2 sine of theta. But the problem with this, even though that this is my final answer for my pole, it doesn't work out. Okay, so it's not actually symmetrical here. So let's go to B. Let's go to my line, pi all over 2. Let's go there. Line pi all over 2. This one said, if I take r and theta, and I actually make both of them negative, what's going to happen? Okay, if I make both of them negative, is it actually going to be symmetrical? So what this means is that I actually just get minus r equals 1, and then just straight up when I plug in the negative theta, I get negative sine of theta, negative 2 sine of theta. Even if I divided by that negative here, it'd be negative 1 and plus 2 sine theta. But that I don't have a negative 1 here. So once again, that's a no bueno. Okay, even though that was my final answer for the symmetry. And then last, I want to do the pole. Okay, so I want to do the pole here. So my pole is going to be r to negative r. Okay, we're just going to change my r's. But if I change my r's, my 1r in the problem, and then 1 plus 2 sine theta, of course, I don't get anything different. So once again, it's a no bueno. So all of these, it doesn't check out, okay, even though that these were my final answers for the symmetry. Okay, so that's unfortunate. So let's now go to my second step, which would be actually figuring out whether it's an inner loop or anything. I already know it's vertical. Okay, so I already know it's vertical, but what's the inner loop? So we take a minus, or a divided by b. So my a here is going to be 1, and my b here is 2. So let's take 1 all over 2. And this is definitely less than 1, which means, since it's less than 1, I have what we call an inner loop. Okay, now if I graph this, I'm just going to show you what it looks like when I graph it. let's just say that this is 1 and then that's 2. What it's going to look like is something like this. Hopefully I'll try to graph this adequately. Something similar to that. Now, maybe you're thinking, okay, Mr. Carlson, if that's the case, it's totally symmetrical to my line. Yes, it is. However, and then you may be thinking, well, but we said it's not symmetrical to my line. No, we said it fails the test. And if it fails the test, it may or may not be symmetrical to that. So that means it could or could not be. And in this case, obviously, even though we tested it out, yes, it failed, it still is symmetrical. Okay? So that means this tells me that it could be, or it could or could not be symmetrical to all of these symmetries. So that is the symmetry applied and also graphing, and then also kind of dealing with what it is. Is it in a loop or not? Could you do a lot of this on Desmos? Obviously. Okay, so let's get to what we call rose curves now, and then I'm going to skip the symmetries for the next. So the rose curves are actually very simple because it's really just these formulas, and the basic pattern here is that if the rose curve has 4 petals, okay, that means your n value, the thing that's attached to your theta, is half of that. So if it's even, it's going to be half of that. So meaning this is an even number. That means I'm going to double the petals. That's the number of petals. So 2 times 2 is 4. For 4, I'm going to double that. If I had, 6 theta, it's going to be 12. And that's something that you should have figured out on the Desmos exploration. Okay? But if it's odd, such as 3, I don't need to do that. Like, I don't need to double anything. It's just 3. If it's 5 like this, it's just 5 for odd numbers. And of course, your A value is the length of those petals. Your A value is the length of those petals there. Okay? So here, I'm just given this. So first things first, I'm not going to do symmetry at all, but you could. I'm just not going to. I look at that, that's 2. And since it's even, I'm going to double that. So 2 times 2 will give me the number of petals. So that means it's just 4. So I know I have 4 petals chilling in here, and that right here tells me my length. So R equals 4. That tells me my actual value that goes out. So it's going to roughly look like this. I hope I can actually get this. Let's actually go to actually 4 here. So it's going to look something like this. Honestly, that's probably one of my best ones yet. Okay, so it's going to look something like that, but minus like the circle around it. Okay, it's not going to have the circle. It's just going to be the petals there. So it's 4 length right here. That's going to be 4. And then there's 4 petals. Good deal? Awesome. Math Excel will probably want you to do the test for symmetry, but I'm not going to do that. And then last, what we have is called lemniscates. So we're almost done here. These are the equations for lemniscates. They're rather odd. Okay, they look like little infinity signs or peanuts. They just never ending. Okay, it is symmetrical with respect to the pole if it's sine, and then symmetrical to the pole and the line pi over 2 if it's cosine. So these are actually really great. So basically, they already tell you what it's symmetrical about. If you get a lemniscate like this, it's automatically going to be symmetrical to these things, depending on if it's cosine or sine. Okay, so I'm going to be given this equation. So basically, what this says is it doesn't necessarily tell you a squared, but I can rewrite this to be r squared equals 2 squared then times sine of 2 theta. So that means my a value is just 2, okay? But either way, it doesn't really matter. I can also rewrite this to say r equals, and then the square root of 4 times sine of 2 theta. And then after you kind of play around with it, you can just plug it in just like that, or you can go right here. It doesn't matter. You just plug it into Desmos, and you get something like this. briefly. I mean, something kind of like that. Okay, and that's symmetrical to the pole. Awesome, 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 sweet. So that is all I have. Let me erase and let's get you started on the summary. So what is the summary? So you learned to recognize the difference between each type of polar equation in this graph. You also probably learned that yesterday during the Desmos activity. How to plot the points and then use those points to graph the polar equation. Use symmetry to graph the polar equation as well. Okay, so remember, makeup tests are due, or retakes specifically, are due on Friday. We will have a quiz tomorrow. That's going to be the polar quiz, and so the polar quiz review is open, and you will get 5 extra credit points on that quiz if you complete the polar quiz at 100%. There is no video attached for that day, so just take the quiz, and that's it. Guys, this has been a blast. One more week of trigonometry. Can you believe it? So one more week. Next week is our last week. 3 more lessons. We are almost done. Until then, see you guys later. Make good choices.